Okay, perfect. So what I will do this lecture is basically an overview. I noticed in the past I made a slide deck. It's like 5 or 6 slides. It basically talks about problem solving, gives you basic steps on it. So these are the slides what we see right now. I tried to upload them earlier. It didn't allow me, so I'm gonna try to upload them again after the lecture. And if that again fails because Blackboard just didn't work, I will just send them per email. Okay. So this will be basically on the slide deck, and later I will just go over some brief stuff that I think is important to know. Okay, perfect. So the first topic that we discussed was bending, and the bending equation is shown here. So first of all, actually, for any of the problems, bending, torsion, shear, what we can do is split up between, say, a non-idealized problem. So we basically take into account the thickness of the structure as is, or we have an idealized problem. So we have booms that basically represent the skin and the area of the skin and stiffeners. So every time we see a problem, the first distinction that we can make is it idealized or non-idealized? And it's very simple distinction. Basically, if you have areas of booms, it's idealized. Otherwise, it's just non-idealized. A couple of other key phrases that can help you distinguish between idealized and non-idealized is phrases like only effective in shear. Say the skin is only effective in shear. That basically means that the skin doesn't carry any direct stresses. So most of the time, that means there's an idealized section. Or this cross section is effective in both shear and direct stresses. That means, at least for the shear problem, we'll get to that. They have to take into account the thickness. And if the problem is effective in direct stresses, most likely it's non-idealized. So what do we know then? So what we do know is that we have a certain bending equation derived. We don't need to know how we derive that equation, but for the exam, it's important that we know what the components of those equations are and what they represent. So first of all, what we see is that direct stress is dependent on the moments, mx and my, and the location at the cross section. So the x and y coordinates, what we see here in these two equations, are both with respect to the centroid. So if we have a non-idealized cross section, and the other parameters that the direct stress depend on are the moment of inertia. So now comes the difference between the non-idealized and the idealized structure. So if you have a non-idealized structure, we have to go with the standard integral equation that we have the integral of over the area of y squared dA, x squared dA, or xy dA. Take into account if we have if the centroid of our segment does not correspond with the centroid of our entire cross section, we have to also include the AD terms of the Steiner, so the parallel axis theorem. So that's important to know. However, if we do have an idealized section, basically what we only have left over is that we assume that the thickness is 0, so the 1/12 h bt squared or h cubed b basically disappears, and we only have effectively Steiner terms. And that's represented by the summation of the boom area multiplied by the distance towards to the centroid squared. So for Ixx, that's y squared. For Iyy, that's x squared. And for Ixy, that's xy squared, xy. And keep in mind that for Ixy, the coordinate system does matter because we don't have a square. That means that if you're below the centroidal coordinate system, it has to be negative. If you're left of the centroidal coordinate system, it has to be negative for y, for x, and below it is negative for y. So let me do that quickly on the board. So again, say for example, this is our coordinates. This is our cross section. We have our centroidal axis here. So what we do is basically we say, well, this cross section is 3 segments. It's our first segment, and our second segment, and our third segment. Because the moment of inertia can be viewed as a summation of the individual parts, we can do this. So for this one, if this is non-idealized, so what we have here is the centroid of our vertical beam corresponds with the centroid of our cross section C. So what we can do it is that 1 over 12 h cubed b. Well, b is the thickness, so in this case it becomes t. So in this case we don't have any AD terms because d, or d squared terms, would be 0 because the centroid of our section corresponds with the centroid of our cross section. So for 2 and 3, here we have again 1 over 12 h cubed b, which is again t, or in this case, if this is, sorry, a, b cubed a, cubed a, sorry. So in this case, the h will be the thickness, and will be thickness to the third, and we always assume thin walled, so this basically disappears, and we're left over only with the AD terms squared. A is in this case the area, that is in this case A times T, and the D squared terms is this distance, this y distance towards the centroid. So if this is h, this becomes h over 2 squared. And we see here, we will get the same thing, that's again AT h over 2 squared. And to be 100% consistent, you have to actually say it's minus h over 2, but because it's a squared, this minus doesn't matter if you add it or not. So that's where, say with IXX, it doesn't matter where your coordinate system is because the squares take care of it. So if we then look at the coordinate system of IXY, and we're going to look at only these two. So we now have to basically say AD becomes A times X times Y. In this case, the Y is negative, the X is negative, so here we get two negatives. So in this case, negative X, negative Y. So they cancel out, and here we have positive X, positive Y. So basically, they don't cancel out, but they're twice as large. Okay, but you can have segments, for example, like this, or in this case it will be symmetric, so it's 0. Let me see, if this is twice as long, let me actually come up with a better example. Yeah, sorry, let's do it like this, where we just flip it 90 degrees, or flip it 180 degrees. We have this. Now, if we look at the AD or the XY, will be A times X times Y. This X is positive, so positive X, and Y is negative Y. Here we have negative X, but positive Y, because this is our centroidal coordinate system. So this is how positive Y and positive X are defined. In this case, you have two negatives, so your XY term will be a negative, and will be basically twice, 2 times. Okay. So it's important for the XY terms to take into account the local coordinate of our segment and how if it's negative or positive with respect to the centroid. And that's invalid cases for both the idealized and non-idealized section. And then, of course, the x and y location that we see in the sigma z equation. So again, just go quickly to the board. So we have sigma z, and its value is a function of x plus a function of y. These two values, x and y, are with respect to the centroidal axis. So if we look at, say, point 1 and point 2 here, in this case, x is positive, y is positive. And in this case, x is negative, y is negative. And if this is h and this is a, and this is a as well, so point 1, it becomes a h over 2, so the xy coordinate system, and here it becomes negative a over negative h over 2, and then of course if we have this one, and then if we look at point 1 and 2 from this cross section, 1 will be negative a positive h over 2, and 2 will be a negative h over 2. So that will be a coordinate system if you want to evaluate for this section, the sigma z at point 2 and 1, and for this system, if you want to evaluate the direct stresses at point 2 and 1. So in these cases, x and y, we'll be seeing the stress equation are the coordinates of where you want to evaluate it with respect to the centroidal axis. Okay. So that's basically over. This is the most variation you can get over bending. And keep in mind, you're getting stresses. So, and of course, if you know an area, you can convert to forces. And then if you know forces and maximum force applied, or if you have stresses, where you can go for failure to compare with respect to the, and make sure it's there. So if you have stresses, you can divide, multiply by area to get forces. Yeah. And then if you have stress as well, and if you know the material properties, you can say something about failure. Okay, just keep in mind, not everything ends at the question of what is our stresses. Sometimes we go to forces to answer some other questions, like what are the axial forces, or we go to stresses to determine when failure can occur. Okay. Then we have, what we actually went to is actually solid torsion. It's in there. We only have to deal with non-idealized section because in solids we cannot reduce to idealized section. In idealization is always thin-walled and open section or closed sections. We cannot reduce a solid section to an idealized section. And the most important equation in this case is the rate of twist and the torsion. I could have added the torsional rigidity equations. Well, actually, yeah, but this is basically it. So in most cases for solid torsions, we go for rate of twist and what's called. And if we then integrate rate of twist, we can get twist angle as well. So if you take d theta dc and you integral, and you take the integral with respect to z, say the length of the beam, which you can get as d theta on one side, and that basically you multiply t times L over g j, and that gives you the twist angle. And again, the twist angle can be a limitation by design or failure requirement, etc. So next section is thin wall torsion. So if you have thin wall, or we assume for thin wall torsion anyways, non-idealized and idealized, it doesn't matter really, because in torsion we assume there's a constant shear flow. So we have to deal with as we say that torsion is equivalent to 2 times the enclosed area multiplied by the shear flow. And again, rate of twist is applicable. It remains the same for both cases. Okay. So let me think about. Yeah, let's do the other one actually. So for open shear flow, now actually again, idealization matters. Again, we can quickly see if we have an idealized structure, yes or no. And we see that, of course, again, the moment of inertia are affected. That affects, again, what we have, how we determine the moment of inertia in our equation. So for the idealized section, if we assume that it can carry normal stresses, direct stresses, axial forces, or axial stresses, that indicates that TD in this equation is non-zero. If we say the skin is not allowed to carry any normal stresses, or it's only effective in shear, that means that the TD is equal to 0. And that basically reduces your equation. So important is, again, go to the board again. Oh. So what we see is that our shear flow, Q, is again function of x plus blah, 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 function of y. First of all, we're talking about open sections, and you always start at an open end. Okay, so this is our shear flow problem. You start at point 1, or you start at point 4. And the reason is because we know that the start point at point 1, Q1, that is equal to 0. So we know our starting point. At 2, so Q2 is not equal to 0, so we don't know. We have to calculate that first, so we cannot start at that point. Okay. So say, and this is of course function of Sy, Sx, and the moment of inertias, as shear forces, moment of inertias. So both shear forces x and y. So what are x and y in this case? So we're talking about non-idealized sections, and there's actually an integral of t dx and t y ds. And these two coordinate systems, x and y, again, are the positions along our cross section. But because now we're taking an integral, we basically need to know all the positions along our segment that we take the integral from. So if we now, again, isolate segment 1 and 2, and say this is length A, then we know that the integral, and we're looking at, let's look at the y component first. So we know the coordinate system of point 1, that's equal to, let's call this 2h in total, okay? So the coordinate system of 1 is equal to a comma h, and point 2 is x is 0 comma h. So now we have to determine a description of x along this whole segment, along segment 1 and 2. So we know that a goes from point 1, goes to point 2, and goes from a to 0. And we know that the length we travel is again equal to the path traveled equal to a. So the path s traveled is a. So now we have to come up with an equation that is valid along any segment along this segment. So at any location along this segment. So that means that x location is a function of s, because if we do the path at this location, so if we say s goes from 1 to 2, say s is equal halfway, we need to know what our equation is. So in this case, x will be equal to a minus s. Because if we now fill in our boundary conditions, so at location 1, s is equal to 0, we got our a, and at location 2, where s is equal to our segment, which is a, we get 0. So we have now come up with an equation for x that validates or satisfies both boundary conditions in x and y. That satisfies the boundaries in point 1 and point 2. So for y, in this case, we know again point 1 is equal to h, and point 2 is also equal to h. It does not vary with s, so in this case, y is just equal to h. So if you now evaluate the integral, and we take, let's assume that t is, the thickness is just equal to t, so you get tx ds. The segment goes from 0 to a, and we get a second integral that's ty ds, and goes from 0 to a again. Let's see, it's on the board again. So what we get here is, we said a minus s, and t 0 to a ds, and this becomes th 0 to a ds. So this integral becomes nothing else than ths, evaluated from 0 to a, and this integral becomes as minus s squared over 2, evaluated from 0 to a. So that's now the integral of our shear flow equation about segment 1, 2. So before we can go from segment 2 to 3, we have to evaluate what the shear flow is at point 2. So we take the shear flow equation of segment 1, 2, and we evaluate it at the path S is equal to A, and then we get our shear flow at point 2. Note, we have here segment 1, 2, and that's just a point 2. And we use this point of shear flow at 2 as starting point for the segment 2, 3. And in 3, you use the the shear flow at 3 as starting points for segment 3, 4. And we can, of course, make our life a bit easier. We can say this is symmetric, so the shear flow of 3, 4 is equal to 1, 2. So, and I noticed in past exams, finding those correct equations for x and y, where we said a minus s and y is equal to just to h, it goes often wrong here. And if this goes wrong, then of course your integral from 0 to the segment length, goes wrong as well. So in this case, a minus s ds. Okay, so that's basically it. We start from one point, which is an open section, and we continue throughout the cross section. So one more thing, actually. Say, and this was on the second midterm. If you have a segment like this, and we have point 1, point 2, 3, and 4. Let's call this 5 and 6. So we can start at we can start at 1.1, 0.2, 0.3, or 0.4 because there's all open sections. However, when we go to from 5 to 6, the start point is equal to, so the start point 5 or 6 is equal to Q1 or Q5 coming from Q15 plus coming in from 2,5. So if this is symmetric, then you can say it's twice, because then you can symmetry say 1,5 is equal to 2,5, so you can just multiply 1,5 by 2. But if it's not symmetric, then you have to come in from this side first, then solve this side second, and then add the total shear flow, a starting point, and then you can continue going upwards. Basically, whenever you have an intersection, you have to come in from all the free edges first and calculate where the start shear flow is or what the shear flow is at that location before you can continue, because you need that point before you can continue to segment 5, 6. So you need to know what Q5 is, the total Q5 is, before you can calculate segment 5, 6. So keep that also in mind. And of course, always try to apply symmetry where possible. Okay, and that's basically it for open shear flow problem. It becomes a bit more tricky when we go to closed shear problems, because in closed shear problems, what we don't know is the starting point. There's no location where the shear flow is 0, so there's no way that we can start. And to make our life a bit easier is we can split that closed section into an open section, and then we can add an open, say the correction shear flow to it. Correction shear flow can be set up using a moment equivalent study or equation. And what we say is that the moments caused by the external shear forces around the point A must be equal to the moments caused around that same point A by the internal shear flows and their contribution to the moment equation. And what we get is then, and we say the open shear flow equation, the correction shear flow QS0, that contribution is twice the enclosed area, similarly like torsion. So what is this? Let's go again to the whiteboard. So what we say is we have a closed section. So we have no location where Q is equal to 0. So we have no good start location. So that's why. So what we do is we make a cut and we say, okay, well, this is equal to an open section. plus a correction. And that correction is a constant shear flow QS0. So we calculate this as an open section. We do our simpletons equation again. And to find this problem, let's say assume that the shear flow is located here as y. We say, well, we choose a point, say the center of the beam. We take the moments around this point, and this is xi, for example. We say this moment caused by the shear force, applied shear force, Sy times psi, must be equal to the moments caused by the shear flows. And in this case, because we take the center, we can apply, that will be actually 0. It doesn't matter. Yep. Is it? Let's see. There will be integral of Q basic times P times ds. Let's see. This one creates a counterclockwise moment. This was counterclockwise. It was clockwise. That's clockwise. This clockwise. That's counterclockwise. Oh wait. Plus 2Q8. So in this case, actually, all the open shear flow sections, these will cancel each other out, so this will be 0. And then the correction shear flow QS0 will be equal to Sy times psi over 2 times the enclosed area. And that will be a correction shear flow. So it doesn't matter. In this case, they cancel out, just how I drew it. But normally all this is known because you solve the open shear flow problem and you have one equation with one unknown. So you can solve this. And then you add the correction shear flow to the open shear flows, and that's your final solution. So things become a bit more complicated when you have a multi-cell section. Because now if you do actually the equivalence shear flow, or the moment equivalence study, what you get is, say we have 2 cells. So we have a correction shear flow QS0, 1, and we have, let's just call it Q1, capital or QI, and then capital 2 Roman numerals. Okay, so if we now do our equivalence shear flow, so we say psi is equal, this is our psi, or this is our psi, our shear force acting somewhere here. So we have our open shear flows, QB times P times ds, and then plus we have 2 times the enclosed area times Q1 plus 2 times the enclosed area times Q2. Correction shear flow for cell 1, correction shear flow for cell 2. So what we now have is one equation and 2 unknowns. So we cannot solve this. So in order to solve this, what we have to do is come up with an XA equation. So what we do is we equate the rate of twist in cell 1 to the rate of twist in cell 2. And if it's 3 cells of cell 2 to 3, and this gives us an additional equation, so another equation. And then we have 2 equations, 2 unknowns, and we can solve for both Q1 and Q2, and then we can add it to our open shear flows and solve the problem. So whenever we have a multi-cell section, we have to go to the correct to the rate of twist of each cell being equal to each other, and then use those X number of XA equations to solve the correction shear flows. Okay, and of course, if we assume in the eyelash section, if we assume that the skin is only effective in shear, then TD disappears, and then our equation becomes a bit easier. And for an eyeglass section, we only assume that the shear flow changes when we pass a boom. So as long as we don't pass a boom, so between two booms, the shear flow is a constant. So again, if we go to our what we had previously, so previously, say we take the C section again, if we would calculate our shear flows, say with red, we'll get something like this. This will be our Q12. We'll go in this manner. This will be Q23 and Q34. So this is our non-idealized section, and if we have an idealized problem, then basically we would have 4 booms here at these locations, and we say the shear flow changes when we have a boom or we cross a boom. So once we cross this boom, we have a constant shear flow. When we cross the second boom, we add some additional shear flow to it, and we cross the third boom. In this case, we'll go down again. So as you can see, the blue line and the red line don't match because we have made simplification and assumed some that between two booms the shear flow is constant. Yes.
Would you ask us to calculate the boom areas, or do you just provide it?
It depends. Sometimes yes, sometimes no. Okay, so that's it. And of course, then you can go ahead and say, well, okay, if we add an extra boom area, then I get a stepwise, so I can get closer to what my true shear flow would be. And if I add enough booms, then you basically get an assumption, you get close to what your actual shear flow. So if your number of booms goes to infinity, then you basically go to the integral format again. So that's the thing about shear flows, using idealized sections and non-idealized sections, and using when we have closed section, then we have to take into account the correction shear flow, and we have multiple closed sections, then we have to take into account the rate of twist. And normally towards the end of the lectures, but we missed like a week or a bit more, we would cover taper. That's not involved in this case. So if you want to know about taper, I think it's chapter 24 by heart or 23. You can go ahead and read that. It doesn't make anything. It's not very complex. And basically what you have to do is decompose the forces in the correct direction and then use those for continue using those forces. Okay. So that was it for the quick problem solving. You can use this on the exam because it's open book, open internet. Hopefully it helps, and I will upload this as soon as possible when I get an opportunity for it. So the next question is, I'll just draw some things in the board where I've noticed going wrong. So, okay. So the last thing that I want to basically talk about is we discussed 3 main topics. And like I mentioned before, it's bending, torsion, and shear. And the reason why we discuss these 3 topics is that most of the aircraft structures and loads, we can decouple to one of these 3, or we can see it as a superposition of the 3 components. Say, for example, we have something like this, a wind box, and we know that the shear force is acting here, right? So one way to solve this is, and I mentioned earlier when I did, say, took the moment equation, equivalence equation around this point in the center, and I said, well, you have Sy times Xi, this being Xi, right? Is equal to the integral QB ds plus 2 times the enclosed area times QS0, right? And then if you do this, if you make a cut in this section in the middle, you will get a shear flow that's like this. goes up here, goes up there, and then it goes back to 0 here. So now if you evaluate this integral, I said, because if you now look at this part and this part, the contribution of this shear flow going this way is basically contracted by the contribution of the shear flow going the opposite way, right? So if this is 0.01 and 2, let's call this 3, 4, 5. So Q01 is basically the negative of Q05 because they're symmetric, but then they go the opposite way. So the moment they cancel out each other, so this becomes basically 0, and the correction shear flow QS0 becomes S times Y times 2A, right? This is what I just said. So what we can see is this problem, and this is a simple problem, so it doesn't make a huge impact, but for more complex problems again, we can say, well, if we have this problem, again, where SY is like here, because this is, say, a double symmetric beam or cross-section, we know that the centroid lies in the middle. So we know this is the centroid. So we can say is I decouple this problem into the SY, into a problem where our shear flow or shear force acting through the shear center. By the way, this is doubly symmetric, so we have the centroid and the shear center corresponding in the middle. So I replace the shear flow, shear force by the movement to act in the cross in the shear center, and I add a correction to it. So this is basically the shift created a moment. So now I have an internal torque of T, where E is equal to Sy times Xi. So if we now do the shear flow equation, we get the same thing, we make a cut, but now we can argue that the location of the cut and what we take the centroidal axis from as basically adds that the correction shear flow is equal to 0. And this torque now adds a new Q to it of say Q0 of equal to T over 2A. And T was equal to Xi times S over 2A. So what we basically did is we moved the shear force to the shear center, and we made our lives a bit easier, but we added a constant shear flow to it, or a torque to it, which creates a constant shear flow. And in this case, the solution will be exactly the same. So this is a very simple problem, but for more complex problems, sometimes moving the shear force and adding a shear torque to it simplifies your life, because sometimes this moment equivalent study can be more complex than this quick trick you do here. Because if you do it correctly and if you make the cut in the right location, we can argue that that this equation, the correction shear flow, by just looking at the shear force, would be automatically 0. We can see that from the structure. And we did an example in the class as well. I think there was one of the examples that we did that had a closed section, basically like a t-shirt, and you had a SY acting in the middle. And based from that, we said immediately, well, symmetric, so all the shear flows on, say, the left-hand side will contract all the shear flows on the right-hand side. And because we make a cut in the middle, we can take the moment equation at the same center where the shear force is applied, then QS0 is 0. So we could immediately see from our from the geometry. And then we can just add, in this case, we can do the same thing and say, well, the torque, because we moved the shear force, we have to compensate that with the torque, and that's equal to the shear flow due to torque is equal to T over 2A. So it becomes a bit easier in some cases. Like this is a very simple problem, but there are more complex problems that moving the shear force and adding a torque to it significantly simplifies your life in the calculation steps. And that's the reason why basically these three topics are discussed. Because even though if you have like a very complex section, like you have a wind box or wing of a aircraft, and say you've given a loading force, so you can basically assume this is a beam. You can look at the loading force given by, say, x squared minus x half x or something like this. So you have a lift distribution. What you can do then is you can, if you want to calculate the shear flows and all that stuff, you can basically create a shear force diagram, a moment diagram, and then based on the shear force and shear moment diagram, you can calculate whatever the bending component is, segment Z, at any location, and what the shear flow is, and therefore the shear forces. Or better said, shear flow, and therefore shear stresses. So now, say for example, you want to have in the middle of the beam, you can calculate based on external loading, you can calculate what the internal shear force diagram, moment diagram looks like, and then you can use those moment and shear forces at those locations to fill in the bending equation and the shear flow equation to get the stresses, and then you can say something about failure. So again, like even if you have a complex, say loading structure on your wing, you can always decouple it to the building blocks that we basically talked about in this lecture series. Okay. Let's see other things. That was basically the first part of our lectures, and the later part we went to idealization and cutouts in this case. So basically idealization is a method to simplify our bending shear flow equation that we saw earlier. So it doesn't change anything, it just makes our lives a bit easier in the analysis step. For cutouts, on the other hand, we have to be a bit more careful. So basically we have to calculate the effect of a missing panel. Say if this is missing, using the average shear flows at the end, the average, what the effect is of the shear flows in the corresponding panel 1, 2, 3, 4, 5, 6, 7, and 8. And we can do that by calculating the undisturbed field by not assuming it, so this is 9, and then getting another panel and saying, well, the shear flow minus 9 is applied here, so we can find the contribution, the effects of that opposite correction shear flow here, to add these two to get a 0 shear flow in this panel, therefore missing, and then we can add the rest to it as well. And this is towards the end of chapter 22, if I'm correct. And it seems complex, but at the end of the day, it often comes down to equilibrium of forces in x, y, and equilibrium of moments in x and y if we do a 2D problem. So even though you see a problem and it seems complex, especially in idealization, and that's unfortunately we did not properly record the lecture last one. So look at chapter, I think it's 22 again, by heart, and what you see is just comes down summation of forces in x and y most of the time. And keep in mind, if you have a boom that carries all the stresses, say you have a stiffener, like in this case we had a panel, say this is the panel, and then we have a boom. Say if we have a shear flow in this case, Q, and we have a force here, so P, then the P will be, of course, in equilibrium with the shear flow in the panel, so P is equal to Q times, this is segment S, because shear flow times the distance traveled is our shear force, so we can always isolate this segment and do again a force equilibrium in Y and find out what that P is actually equal to minus QS in this case. Okay, I think this more or less what we all covered in this lecture series. And I think together with that, the slide deck that I'll upload later today, will give you a good opportunity to do the exam well. Like I said earlier, 4 questions. I don't think it's that hard. So is there anything that you guys want to discuss in the remaining 15 minutes?
You have a fun semester?
Me?
Yeah.
Always have fun. So anything specific related to the course? Anything that you guys think is difficult? All right, one more thing. I think at the end of each semester, you guys get basically a review, the evaluation. If you can fill that in. Since last year, so I never bothered to ask it. I think only 5 people have ever filled it in, and they bother me, so I bother you guys. If you can keep, I'm satisfied that you guys will be satisfied as well. So yeah, just fill it in. It's anonymous. I get the final results, but I don't get individual results, so don't worry about it. If you have feedback regarding the course, also those online. Just email me if you want to talk. If you want to be upfront about it, or like if you don't mind me knowing who's talking. Otherwise, just use the evaluation form, and I will just implement that in the next semester. So other things that you guys want to discuss? No topics? Okay. So exam will be opened on Friday 9 a.m. It's automatically set. I've uploaded everything. That's Sunday 9 a.m. Sorry, not Friday. And I will close at yeah. I'll close on Tuesday 9 a.m. So you have 48 hours. I think a couple of hours should be sufficient. When you upload it to me or you send it to me, please check if it's readable. And please check if you've uploaded the correct document. I think in the past, I had one document I could not open, and another person uploaded the wrong document. So don't shoot yourself in the foot. Double check it. Check if it's readable as well. Like, I know a lot of people do everything by pencil. So make sure, sometimes you can play with the contrast of it. Just play around with the contrast, make sure it's readable for me. And because if I have to guess, it's always annoying. And you might lose out points where it's not needed. Other things, always write down the assumptions you make, clarify things. Like simple things are like, okay, this is symmetric, therefore IXY is equal to 0. Stuff simple like that. Just clarify it very briefly. It's not going to take a lot of time, but helps me with the thought process. Also, what I always advise, if you say if again, simple stuff or like any geometries, so you have to calculate the moment of inertia of IXX, right? And you have given, say this is A, and this is 2H. Okay, and say you've given numbers for A is equal to 10, H is equal to 20, blah, blah, and T is equal to 1. So if we now look at the moment of inertia, so you have 1 over 12, H cubed B, H cubed T, this will be 2H cubed plus AT times H squared times 2, right? So I've noticed a lot of students, though, immediately plug in the numbers and give me something like, say, moment of inertia is XX, and it's 1 over 12, and it says 20, so there's 40 cubed, plus times 1, plus 2 times 10 times 1 times 20 cubed. This is totally fine, and you give me, say, final answer of 7 millimeters to the power 4. So it's harder for me to realize if we made a mistake here. Say, for example, if this is instead of 2H, you did like 20. It's a bit harder for me to understand what went wrong in the final solution than if you just give me the variables first and then plug in the numbers. So I know sometimes it's annoying to work with variables, but often it's very simple to figure out what went wrong. Say, for example, if you had an H here, then I'm like, oh, the total height of this segment is 2H, and he or she just plugged in 1H. So I know immediately, okay, that's a source of error, so it's for me easier to figure out instead of by the numbers. I have to go back and see what numbers, especially if like multiple numbers are the same. I don't know if you used the wrong dimension or something else with one. Okay, so it helps yourself to remain consistent and clear about it. And if you like, if this is the page and this is the end of your page, don't try to plug in everything again on this side and then be like, man, 7 is that. Because just use extra line on space. It helps you, helps me because it makes more clarifies everything else. Another thing, start out over on a new page every problem. At the end of the document, just fill in 1 out of 5 pages, 2 out of 5 pages. Because then if something went wrong with your scan, I often check it before the deadline, then I can quickly come back to you saying, hey, you're missing page 3 out of 5. And you said it's 5 total pages, but I only got 4. Stuff like that. So maybe you don't notice, maybe you check, you scroll down, you see, oh, everything is readable, let's send it out. And you didn't notice that only 4 out of 5 pages were uploaded. At least if I notice this before the final deadline, I will email you back saying, hey, double check of it, can you send me an updated version? It just helps you. Other things, yeah, I think I requested to have, I think, last name, first name, your CID. Please stick to that format. It helps me when I plug in numbers. I can sort it by last name very easily, and I can just plug in the numbers correctly. That's it, actually. So I hope you had a good semester, and like I said, exam will be uploaded automatically Sunday. Next Tuesday there will be no lecture. I'll try to get everything out by the end of the Tuesday, hopefully. If not, before noon Wednesday, hopefully. Then we can have a Q&A about the exam on Thursday. If there's interest for it, I'll be here. I'll wait 10-15 minutes. If nobody shows up, then I'll just leave. And then the resit exam will be available on May 2nd. That's Sunday, yeah, May 2nd. Keep one more note. Both Sundays, so upcoming Sunday and next Sunday, May 2nd, I'll be probably on travel, so I will probably not be able to answer any emails on Sundays. I'll try to, but because the deadline is both times on Tuesdays, I can always get back on a Monday to you guys, okay? Okay, perfect. Thank you very much, and have a good exam.